from C-DAC India. As I was telling, last year, we had the first presentation from C-DAC. His colleague had come. So to introduce him, Mr. Rakesh has been associated with the Center for Development of Advanced Computing called C-DAC since 2006. He's currently serving as a scientist in the HPC Technologies Group, where he leads several key initiatives in system software development, particularly for the Trinetra network. That is the network they're designing there, and he will be talking more. His work also involves the adaptation of MPI libraries for Trinetra. His primary areas of interest include HPC, parallel file system, programming models, performance tuning. He holds a Bachelor's of Engineering in Information Technology from Maharana Pratap College of Technology, Gwalior, India. So I have actually visited multiple times to their facility, starting many years back, and periodically they have been developing over the years, different kinds of adapter, different kinds of switches. And so today you'll be talking about MVAPICH4 over C-DAC's Trinetra network. So let's give a big welcome to Rakesh.
Thank you, Dr. Panda, for providing me the opportunity to speak at this MUG conference. So my name is Rakesh Kumar Yadav, and today the title of my talk is MVAPICH4 over C-DAC's Trinetra network. So here is the outline of my talk. I will give a brief introduction of Trinetra HPC network. Then I will talk about the software stack which we have developed for Trinetra network and what features it provides. Then what middlewares we have adopted. So basically MPI is the main middleware which we have adopted for communication with the Trinetra network. And then I will talk about the benchmarks which we have used for validation and few configurable parameters of the software stack, how they are impacting MPI point-to-point and collective communication. Then I will talk about the HPC applications from different domains which we have tried over the Trinetra-enabled clusters. We have also started basic experiments with AI frameworks. So I will talk about those. And we did basic experiment of MVAPICH4. We have tried MVAPICH4 on RISC-V architecture also. So we have one slide for that. Then what future plans do we have? And finally, I will summarize my talk. So I will begin with the introduction of the Trinetra HPC network. C-DAC is a premier R&D institution which works in various domains. HPC is one of them. And C-DAC has a long history of developing HPC network. So currently, we are working on these two products, Trinetra A and Trinetra B. So Trinetra A is on the link side, it is 100 gigabits per second speed. It provides this speed. And it is a FPGA based card. It's not ASIC actually. So on the host side, it has an interface, PCI Gen 3 exit interface. So it is a direct network. So there are no external switches involved in this. Here you can see it provides 6 links through which we can configure Torus network. The next product is Trinetra B, which is recently we have developed. And it provides, on the link side, it provides 200 gigabits per second speed. It has got PCI Gen 3 X16 interface on the host side. And again, it is also a FPGA based card. So here you can see it provides 10 links through which we can configure multiple topologies like Mesh, Torus, Dragonfly, etc. Now I will give the introduction of Trinetra software stack which we have developed. So here you can see this is the diagram of software stack which we have developed. So on the left-hand side of the stack, you can see this is a high performance path for MPI based applications. So here you will see we have employed kernel bypass mechanism for data transfer operations. So there is, it can be understood by an example. Let's say whenever an MPI message comes, so it will be directly given to the hardware. So this is a slow path actually. So in the later part of the presentation, I will explain it. So what software stack features this stack is providing? Whenever a network, when we talk about the network, so basically you need to provide transport functionalities. So those transport functionalities can be performed on the CPU. If you are performing those functionalities on the CPU, then it becomes an on-load approach. If you are performing those on the hardware, so it becomes offload approach. So we have adopted hybrid approach. Through an analogy, I will explain it. Whenever an MPI message comes, so it will be divided into the segments. We call it packets. So those packets will be given to the hardware. So internally, hardware also divides those packets into fragments, which will be equal in size of hardware MTU. So the management of the fragments is done by the hardware, and the management of the software packets is done into the library. That is why we are saying it is a hybrid approach. Here is a list of functionalities which are performed by software stack. So this provides a reliable data transfer communication through retransmissions and acknowledgements. We have used adaptive flow control based on the send credits. As I said, the message will be divided in the packets. So packetization will be done by the software stack, and the assembly of the packets will be done on the receive side. Since it is a torus network, so packets may come out of order. So we need to implement out of order packet handling. Since we have implemented out of order packet handling, so in order message delivery is guaranteed. On the receive side, messages are delivered based on the tag matching. So that we have employed here. Earlier, I talked about the kernel bypass mechanism it provides. The next slide is continued slide for software stack features. So it is, as I said in the previous slide, whenever a message comes, we divide this message into the packets. So this is a configurable parameter in the software stack. You can configure software packet sizes like which starts from 1 KB, it goes up to 32 KB. So in the further slides, I will show you how this configurable parameter is going to affect large message size bandwidth. So there are two basic protocols which we have developed to transfer data. So one is single fragment queue, which is SFQ, and mainly it is for the small length messages. In this protocol, we deliver data on the send side through PIO mechanism. The second protocol is eager protocol, which is mainly for the transfer of medium and large length messages. So in case of eager, whenever a message comes, so it will be divided into the packets, and those packets, some control information of those packets will be given to the hardware through PIO mechanism. And based on that control information, hardware will read the payload, packet payload through DMA on the send side. And both the protocols on the receive side will deliver the data through DMA into the intermediate buffers. From those buffers, data will be copied to the application buffers. So as I said, there are two protocols. Then the selection of those protocols is based on the threshold value, which is nothing but a message size. So about this also, in the further slides of the presentation, I will show you how this, how the variation of this threshold of protocol switch affects the point-to-point and collective communication. We have a latency optimized path for tiny packets, and we have used OFI interface to run MPI over the Trinetra enabled clusters. So till now, I have covered left-hand side part of the software stack. Now, on the right-hand side path, which we are calling slow path, because it is just for run legacy applications which uses socket interface. So that socket interface or enabled applications also can be run over our network. So it uses IP over IP component of Linux kernel, and we have validated this through various benchmarks like iperf, netperf. We have also used file IO operations through NFS, and we have also run OMB benchmarks using MVAPICH4 on the slow path also. So till now I've covered software stack and what features it provides. Now we want to run HPC applications over Trinetra cluster, then we need some middleware. So we have chosen MPI. So what MPI support we are providing? MVAPICH4 is the primary MPI implementation which we are using to run scientific applications. It uses OFI interface. We are also trying to adapt MVAPICH Plus to run AI frameworks. Since we have a long association with MVAPICH team, we have received very good support from the MVAPICH team to run all these MPI implementations. As I said, we have used OFI interface, so we are also able to run other MPI implementations over Trinetra cluster, like MPICH, OpenMPI, Intel MPI. These are also we are able to run. So now, what benchmarks we have used for validation purpose, and how the configurable parameters which I talked about in software stack features, so how they are impacting the MPI applications that I will cover here. So before going to the benchmarks, just a brief information about the test beds which we have used. So we have two test beds. One is Trinetra A network-based testbed, which is a 24 nodes cluster. Here Trinetra A is configured in this 2x2x6 3D torus topology in this testbed. The next testbed is for Trinetra B actually. So it is a 12 nodes cluster. Here it has a topology of 2D. It is using 2D topology 4x3. So we have tried all these things, what benchmarks and applications on these two clusters. So here is a list of benchmarks which we have used for validation and benchmarking purpose. We have tried OSU MPI benchmarks. We have run Intel MPI suite. We have also tried NAS, HPL, HPCG. Along with these benchmarks, we have also tried applications from various domains. So recently we are able to run this NAMD application which uses Charm++. So here is the micro benchmark results of what latency figures we have received for small length messages as well as for large length messages. So here you can see Trinetra A provides a 2.1 microsecond latency, and Trinetra B is providing 2.4 microsecond latency. For small length, you can see Trinetra B is giving slightly higher latency. The reason for that is Trinetra B uses FEC block, which has its inherent latency and which cannot be avoided. So here is the bandwidth comparison of Trinetra A and both the products, Trinetra A and B. So Trinetra A was providing 4,554 megabytes per second. Now Trinetra B is giving around 10,000 megabytes per second. As I said earlier, I have said that we are able to run multiple MPIs over Trinetra clusters. So here is the comparison of latency figures. We have tried MVAPICH 4.0, OpenMPI, MPICH, and Intel MPI. So this is for small length messages. So here you will see Intel MPI is giving slightly better performance, slightly, for the small length messages. But if you compare for the large length messages, MVAPICH and Intel MPI both are performing same and better than the other MPI implementations. So during stack features, I talked about two configurable parameters. One was software packet size. So in this slide, you can see how the different values of software packets are affecting the bandwidth for the large length messages. So here you will see this is software packet size 1K and it goes up to 32K. So you can see the large packet size is giving better performance for large length messages. In the previous slide, I talked about the how different values of software packet size are affecting the bandwidth. Similarly, in this slide, you will see the second parameter which is configurable is the threshold for protocol switch. These are the two parameters which we have tweaked. So in this slide, you will see we have used 5 values for threshold of protocol switch, which is it starts from 1 kb to and goes up to 16 kb. So basically the range of message size which will be affected here will be from 1 kb to 16 kb. The reason for that is whenever the message size will hit the threshold value, so protocol switch will occur. So you can see here before 1K, all threshold values are giving same performance because all messages are being transmitted using same protocol, which is SFQ protocol. Similarly, from 16K onwards, you will see all are performing same because they are all using same protocol, which is eager protocol. So the deviation in the performance is only from 1K to 8K. And here you can see in this message length, the small length threshold values are performing better than the higher values of thresholds. And the reason for that is whenever you are transmitting large length message through SFQ protocol, so it has an overhead of packetization. That is why the small length messages, small length thresholds are performing better than the large length thresholds. Here you can see the impact of this different threshold values on the bandwidth. Here larger is better, and here smaller was the better. So the same variations we did of threshold values for protocol switch, and here you can see how it is affecting the MPI all-to-all communication. So you can see the smaller thresholds are performing better for a specific message range, which starts from 1K to and goes up to 8K. At 8K, you can see the smaller thresholds are much better than the higher threshold value. Here we have used 16 process per node, and we have taken this reading on the 16 node cluster. The same variation we have tried with MPI all reduce also. So here you will see the smaller thresholds are performing better than the higher thresholds for all message lengths. And the reason for that here is what we have observed in the software stack. Of 8K onwards, MVAPICH, this algorithms of MPI already reduce will start dividing large messages into the smaller ones. And we have already seen for the point-to-point communication, the smaller thresholds perform better. That is why you are seeing the all small length messages are small length thresholds are performing better for all message lengths here. This also reading we have taken on the 16 node clusters, 16 ppn per node. The same variations we have also tried with HEFFT application. Here we have used problem size as 128 cube, and the backend which we have used for HEFT is Intel MKL, and the MPI is MVAPICH4. Here you will see the smaller thresholds are giving better performance. These are gigaflops per second. So higher is better here. Whereas this 16K is performing less, giving less performance. These are the readings with socket-based applications, which we have tried on Trinetra B network. So we have taken file IO over NFS. You have a random read and random write bandwidth here. We have also tried OMB. So OSU latency and OSU bandwidth is given here. We have tried iPerf and NetPerf. So next part is applications from various domains, which we tried over the Trinetra B cluster. Actually, in this, I'm going to give the performance figures only for Trinetra B, because last year we have already presented Trinetra A. So these applications we have tried over 12 nodes cluster. As I said, we are able to run this NAMD application, which is from molecular dynamics domain application. So here you will see this blue line is representing performance of Trinetra B, whereas this is this red line is the hypothetical linear scaling. So we are, as we are increasing the number of processes, we are deviating little bit. So we need to tune our network or software stack, so that this both the lines can coincide. So this quantum espresso is quantum based application from the quantum domain, which is used for nanoscale modeling of materials. So here you will see, as we are increasing the number of nodes, the execution time, wall time is decreasing, which is almost linearly giving linear scaling. This is a LAMPS application. Again, it is also from molecular dynamics domain. So here you will see, as we are increasing the number of nodes, so the time, wall time, execution time is decreasing. This is also SysAcomo 2D application, which is a seismology application, which is used for modeling and analyzing seismic wave propagation behavior. So the same observation with this application also we are able to see. Now I will talk about the basic experiments which we have started with AI frameworks, because we want to run, we want to see the observations in a heterogeneous environment, how Trinetra is performing. Even though these are very basic experiments which we did, we only have a 4-node cluster. Each node is having a NVIDIA A100 GPU with 40 gigabytes of memory. And we have tried hovered with MPI. So here you will see, as we are increasing the number of nodes, we are scaling linearly. So ResNet 50 model we have tried here. Next, in earlier presentation of MVAPICH, we have seen that PyTorch 2.0 has been released with MVAPICH support. So this also we have tried over our cluster. So here, we tried with only two nodes. Each is having a NVIDIA A100 80 GB card. So we have tried GPT-2. So as we are increasing number of nodes, since we have already 2 nodes here, so the time is decreasing here. So next, this we tried MVAPICH on a RISC-V architecture. It is very basic experiment actually. Here you will see we have used this Star 5 Vision 5 board, and it is having a Fedora for RISC-V architecture. On this we have tried. We have successfully compiled MVAPICH, and we have also tried benchmarks like HPL and HPCG on that. So on this, we have a poster in cluster 2025. So you can see the detailed. Now, what future plans we have? So in a month or two, we will get 128 nodes cluster, which will be having a Trinetra B as a network. We are also trying to optimize Trinetra's software ecosystem to enhance the performance of HPC and AI applications. And we are all open to collaborate with the HPC application developers so that we can optimize the performance of the software stack as per their requirement. So finally, I will conclude here. Here is the summary of my talk. Trinetra is an indigenously developed network. It has a feature-rich software stack which can be customized as per the requirements. MVAPICH4 is the primary MPI implementation over Trinetra-enabled cluster. And we have started experimenting with the AI frameworks. Thank you.
We have time for a few questions. Any questions here? So I have one question. So is this network is only for Indian market, or what is the plans kind of thing?
Actually, we have, as I said, it is a FPG based cards. So currently we have a very limited size of clusters, but in future, let's say next generation Trinetra will be ASIC based. So we do have a plan for market.
Like both inside India and outside also? That is a question I was going to ask.
Actually, that I'm not aware actually how the decision will be taken.
Okay. Yep. Any other questions for Rakesh? Any online questions? Okay. So let's thank again Rakesh.
Thank you. Thank you.
So we'll go to the final network talk of the session. After that, we'll have the student talk. This one will be presented by Dan Mihalescu and then Winston Liu from Keysight. Let's get them settled here.